project I'm going to show you today is a new thing we're introducing to our scientists, and we're using the ChemAxon cartridge and the Markush search functionality in a way which is a little bit different than what was described this morning. That's why we thought it would be interesting to present what we're doing. The application we are deploying is about tracking chemical series for project teams. This is a problem we're trying to solve. When medicinal chemists work in the project, when they make compounds and they test compounds, they tend to organize these structures into series. A compound is considered to belong to a series if it contains a particular substructure or a scaffold. And so they do their SAR, they talk of these series, they give names like this is the pyridine series, this is the pyrazole series, and they know where they got the idea for that series, what was the first compound that started the interest in that series. They know what problems they encounter with each of these series. Some of these are successful. They lead to successful candidates. Many of these are not, so they get discarded at some point. This is all knowledge that is really clear to the scientists on the project team, but it is difficult to discover for their colleagues that are working on other projects. And even for the team itself, when they've been working on something for years, and you go and ask the question, but how did you come up with that? And sometimes it's not really easy to reconstruct the whole story, where they started, where they went, and all the things they tried. This is something that's interesting when a new scientist comes along and they need to tell him what they've tried, what they've done. Somebody needs to take the time to do that. And so basically, this is all knowledge, which would be really interesting to capture, to make it discoverable and searchable. But at this point, it just stays with the scientist or in some PowerPoint slides that they present at project meetings, and then they're in, I don't know, SharePoint or some shared drives. This is taken from a paper that came out recently, actually after we had already started with the project. And the authors here are nicely explaining how this type of information is really difficult to find even in the literature. So what they show here is these dots are compounds. These are the starting points for the different series. And these are the first compound and what they went next and the next and the next. And some of these led somewhere. This one in particular was a successful candidate. This other one, oh, is this a pointer actually? No, does it? Yeah, so this one terminated. They had some problem with this, and they didn't go anywhere. And the literature that they find usually tells about parts of this story. So you have papers that show SAR around a particular lead. There's papers that will show you a cross-section, the latest development for a particular project. There's some papers that tell you a story. They make it look like a linear thing, but in reality, it is not. It's really hard to find something where you can see all the things that a team tried, and especially the ones that didn't work. So this is something we want to try and address with our application. So going back to the idea of the series, what you can see here you can consider this as 3 different series. This one started here, went up to here, this one started here, and this one started here, didn't really go anywhere. So this is where the idea for this new application came from. We decided to provide scientists with a shared space to store the definition of this series and the scaffolds that represent the molecules in this series, along with some interesting compounds, the most significant compounds, which we call favorites. These structures should be searchable within the application, but should also be available from other systems that we have via web services. And finally, sorry about that, we want them to annotate their structures. So they enter the scaffold, they enter their favorite compounds, and they say something about them, why they made them. and so that we can capture the evolution of the project. Now, just as an aside, I'm going to show some structures here. These are not our new compounds. These are taken from literature, and they were extracted from Campbell. So before I show you the user interface, what you're going to see is a web application, which is built using Bootstrap and jQuery. We're using ChemDraw to enter structures, and we're using our own structure rendering toolkit, Avalon, for displaying structures. And then there's connection to multiple of our Libre services. Their service layer is in Java, and we're using RDKit for structure validation. Finally, in the backend, as I was telling you before, there's the JChem cartridge in Oracle using the Markush search functionality. Okay, so when you go into the application, the first thing you see is a list of projects. Then you click onto one of these projects, and you see this. So this particular project, we've got 3 series. These horizontal boxes are series. And these are described in terms of 2 different kinds of structures. There's the scaffolds. These are the gray ones, the ones with the S, that can have Markush features. They don't need to, but they can. And these other ones are compounds. These are usually compounds that the scientists actually made and tested. So there's 3 series. And for each of them, we actually have a detailed page with some additional information. And then when you click on one of these structures, so you click, for example, here, you get to a detailed page. And this is where you can add annotation. And so obviously, you have a structure, and there's then information about the source. I'm going to tell a little bit more about the source, because we put some effort into allowing scientists to capture as much detail as possible about the source. This is interesting for us. We want to know where our good compounds come from. Do they come from a screening? Do they come from literature, from a patent, somewhere else? This is something we would like to be able to capture. There's links. This is obvious. This is URLs. They can add links to whatever they want that would have on the internet or intranet that adds information to this. Then there's tags. The idea of tags is having a controlled vocabulary to annotate these structures. We came up with a list together with some chemists, and for many of these properties, there's a traffic light system. So you could say this one here, for example, target selectivity is low. You could say this one has good activity. There's a whole list that contains ADME, activity-related, toxicity, and and also about the status. So if it's a front runner, if it's the latest, and best compound that we have at the moment, and all that. And this is not replacing data capture. Of course, all the data is in our data capturing system, in the data warehouse. This is about letting the team give a judgment on the compound, whether solubility was good enough. So for a team, it's not about the absolute solubility value, it's just that solubility was green for that particular target in that particular context. Or you could highlight, oh, here we're having selectivity problems, and so you just put this tag. Then whatever cannot be captured with tags is captured with notes. So this is just free text. And then this thing in the middle is what we call the path. So as in this graph that I was showing you before, taken from the literature, we are asking scientists to define relationships among structures. So this was the starting point. From here, they went to explore this whole scaffold space, and they can give a reason or some rationale behind why they went from here to there. And then from here to here to here, these things can become very long. And but they do build the path from where the series started to where it ended, and how they came up with this. Okay, so now a little bit more about the Markush features. So this is a scaffold, and you see it's a scaffold because we're using, for example, atom lists here. And there are several features that we're allowing our scientists to use when they define scaffold. It's not all the features that ChemAxon supports. This is because we need to find the intersection between what the cartridge can do, which is actually a lot. Then we have our rendering tool, which can do some. And then there's ChemDraw, who cannot sketch everything correctly. And then there's the other system we want to integrate with, which are using other searching engines, which are not the ChemAxon cartridge, which don't understand all of them. So at the end, we needed to come up with a subset of features that we allow to be entered. And this is what we currently support. So list, any atom, heteroatom, R groups, bond types, bond topology, and these features down here are not supported at the moment. So when they enter a new compound, they will enter the structure. And so this is all the other annotation I was showing you before. They add the source, they add the relationships to another compound, tags. And then when they try to enter a feature that we do not want them to use, we have a system to check. So this is using RDKit to make sure they only use the structures, which will then be compatible with all the other systems we want to connect to. Right, so this is a little bit more detail about the source. As I was telling you, we want to capture this. There's a lot of interest in having information about where our good compounds come from. And therefore, we support entering an assay as a source. So you can type the name of the assay and pull it up and link to that assay. It's ELN concept statements, so where they highlight, where they describe the rationale, the ideas they have, they can link to that. And we have a web interface to our ELN that can show all the details. Then there's patents, if they want to say this came from a patent, or literature where they can actually search for papers like you see here. Right, so once all the information is in, then we have a simple user interface that allows for searching. So we can sketch something, and then we find in the search both compounds and scaffolds that match this particular substructure. The search can be combined with other criteria, so you could actually say, I'm going to search for this substructure, and I want a specific tag, so I want just the ones that are active in vivo. Right, so this is what the status of the application is currently, and we deployed this last year to our scientists. And when we present this system, everybody thinks it's a really good idea to capture this knowledge. Oh yes, we need to do this, and this is going to be great once we have all this data. Just imagine what the kind of data mining we can do. But the first thing is to enter the data. So this is a little bit of work for the chemist. He has to go there and just take the time and put in the interesting compounds. At the moment, while they're working, they think, yeah, I know this stuff, I don't need to put it in. But if they don't put it in, then we don't do any data mining. So we're trying to think of creative ways to make it interesting for the project teams to enter this information. And we're thinking that one important aspect is to make it easy for them to enter. So this is one thing. And the other thing is to allow them to reuse the information they enter in this application from other systems. So this is what I'm trying to show here. So this compound series and favors application is in the middle and is connecting to other systems we have. Dart is the web application we use to search our data warehouse. So what we're doing is we are letting scientists send compounds from here to here, and I will show you a little bit more about how we do that. And also what we will do is we will let them pull scaffolds from here to use in substructure searches in here. The HTS Explorer is another web application we have built in-house to look at HTS data. So this is a place where they could identify starting points for series. So we also want to be able to send starting points from here to here. Then there's PowerPoint. This is about exporting the graphical view, which, by the way, currently is quite simple, but we are putting a lot of effort in making this also really nice so that they can use it in presentations. There's CAS. This is something we use for the teams to think about what they should do next. So idea generation, basically. And then there's Spotfire. So I'm going to show a couple of examples of this. One of these is Spotfire. Spotfire, our Spotfire has, we have built in some chemical intelligence with something we call the NIBR chemistry toolkit. It allows to do lots of chemical things, among which is also a multiple substructure search. So you can actually define a list of compounds or structures, you want to search for, and so far it would be some folder with more files or an SD file that you upload. And what we've added now is the possibility to pull structures from the compound series and favorites application. So what you do here is say add items from CSF, then you select your project, it shows you the series, and then you say I want to pick up all the scaffolds for my project, add them to Spotfire for me, and then they show up here, and then you say run the search, and searches your Spotfire, your data in Spotfire for all these various structures, and finally allows you to do visualizations where you tag your data by scaffold. You can highlight by scaffold, color by scaffold, all that type of scaffold-related SAR analysis. This is about integrating with our data warehouse. This is Dart. So here you run a search, and then you find compounds that you think may be interesting to look at. And what we do is now we can highlight the ones we want to send to CSF. So you say, I want this, this, and this. And then there's a button that you click, add these to CSF, and this pulls up this pop-up, this widget that shows you the compounds you just selected. You can add annotation, so you can say this has to go into the D4 receptor in this series, and add this annotation for me, and then add the structures. And then this window closes, you stay in Dart, and then in the background, it goes into CSF and puts them into a series for you. So you stay in the application where you are, you continue your work, you don't need to copy paste, open that other application, put it in there, save, and all that. Right, so this is where we are. We are now working on these integrations, the one that I've shown you, plus making the graphical representation nicer, because another one of the integration we want to do is the PowerPoint integration for the graphical views. And I want to thank the team that worked with me on this. This is these people. That's Manuel is the tech lead. Rekka is the user interface, user experience designer. These are the developers. And then these other colleagues at NIBR that helped with collecting requirements and testing. And thanks for your attention.
Thank you for your talk. The scaffolds, are they manually inserted? So does somebody have to sketch the scaffolds, or are they derived retrospectively from the members of the series using MCS, for example? Yeah,
no, currently they are sketched. But it is a good point. We may think in the future of having some sort of scaffold suggester.
Yep.
So that you say, this is my series, and suggest a scaffold, and then the chemist looks at it and says, yeah, that's it, or no, maybe no. Yeah. Just delete that little piece and that. Yeah. That would probably also help too. Because not everybody is that expert, especially when you ask them to use Markush features. Yeah. Some people like to do that, others, they don't really know how to do it.
Thanks. Yeah.
You have my sympathy on trying to get chemists to engage with anything which has got a long-term delivery. So good luck trying to get them engaged. When you move between the nodes in terms of making progress, is there any part of your system that's capturing how many compounds were made going in a particular direction, or how long it took to go in a particular direction?
No, but that's an idea. Yeah, we could I think we could do that. Well, the time dimension, we could use the registration date for that. And of course, if it's a scaffold, maybe it's a bit more difficult. But between compound A and compound B, we could probably calculate how many compounds they made in the meantime. Is that what you're...
Yeah, just...
Or did you have a better idea how to do that?
Not in our system, no. Sorry, Rich.
There's a fair degree of subjectivity. Do you ever get disagreements between chemists, or is it only one chemist that does it per project team, or how do you handle that?
You mean chemists on the same team disagreeing on what?
Yeah, does that happen?
Not so far, but we do allow more than one person. So there's a concept of the project editor. So once you define a project, you can say who's allowed to edit, and then they can all contribute. But why would you think they disagree? Oh no, actually that's not the first one. That type of thing, or? Yeah, there's a lot of subjectivity there. That's actually the beauty of it, right? You want that knowledge that is in their heads, which is not the numbers which we have already in the data warehouse. So it's possible that sometimes. Also, the data quality is different from project to project because some teams put more into it, some people don't bother, and the granularity of the data is also different from team to team. We don't ask them to put every single compound, but also which ones they put, which ones are considered worth reporting. That's also up to them so far. We left it pretty open to see what they do.
So I think it's interesting to, you say to people disagree. I think actually it's also interesting that if you wait long enough, the story that you hear will not quite be the truth. It'll be, make it look much nicer.
Yeah.
And it'll be quite interesting to go back to look at all compounds made in a project, divide them over time, cluster them, auto-generate the Markushes, and see what the reality of the change in the Markush was over time. And hopefully you would start with more and go to fewer. And you should presumably see towards the end of a project, one quite tight Markush.
Yeah. This is the problem we also have with the retrospective. So we've asked them for examples of stories, and there it's really, it almost looks like a straight line, but it never really is. And we are hoping that they will, if they use it regularly before they know what the end is, that they will also capture series that did not get anywhere.
I refer you to Stephen's
Are you doing this with live projects?
Yes.
You're doing it going forward?
Yeah.
Because I think when a project ends, the story, the narrative becomes much more flattering for the chemists who do the project.
Yeah, no, we are hoping, we are encouraging them to use it as they're working. That's why we also doing this integration with other systems they're using, so they can use the scaffolds or put the structures while they're looking at at their assay data, because we would like to capture the real life and not just the beautiful, the straight line to the clinical candidate.